example. So you consider the complex plane. And say you want to plot a particular, not quite meromorphic function. So you want to say, maybe I'll write this as x minus x1, x minus x2, where x is some complex coordinate. And how do we plot this? Well, this isn't a globally defined function. And so between x1 and x2, the idea is that there's going to be some kind of branch cut. And if you go along the branch cut, and in particular, if you
mean f of
around,
x? You mean f of x or
sorry, yes, yes, absolutely. So this should be a function of x. So if you go around one of these points and go around the branch cut, you pick up a minus sign. And so f is some function from, say, the Riemann sphere. So if you include infinity as a point, it's a function from the Riemann sphere to the complex numbers. So the question is there a surface such that f extends to a function on that surface? So maybe we call it like f twiddle, that is globally defined. And the answer lies in these covering maps. So you have to consider a function gamma, which goes from some surface to the Riemann sphere, such that if I take the composite map, so if I take the composite map, f composed with gamma, then this function is well defined on sigma globally. So it has no monodromies, no anything. And the property that gamma has to have is the following. So you have to have some, let's say the coordinates on sigma are given by z instead of x. Then gamma basically has to have the asymptotic behavior that near zi, for instance, it has to go like xi plus basically z minus zi squared. So then if you consider the function f of gamma of z, and you take z close to zi, this function actually becomes well-defined. Basically because this square here will cancel in the square root. And so this is the general motivation. So now when you're considering twist operators, say in the symmetric orbifold, corresponding to single twist cycles, that corresponds to putting an operator here and some cut, so that when you go around the cut, you pick up not a minus sign, but some monodromy, e to the 2 pi I over w. And so the corresponding covering map needs to be one which looks like, which goes to this point xi, and then has a critical point of order w in order to cancel the monodromy coming from going around this loop. So this is sort of the general motivation of how these covering maps work and where they come from. So now just a couple of facts about these. So fact one, if you have some covering surface, you might say, okay, well, take some point on the sphere and ask how many times or how many preimages does it have under gamma? So say the surface sigma is here, it lies over the sphere. How many preimages does it have? And that number, if you count with multiplicity, is going to be constant everywhere, and it's n. And the fact is that n is given by 1 minus the genus, plus some corrections given by the critical points. And this is on the problem sheet. This is the Riemann Hurwitz formula. And one immediate result of the Riemann-Hurwitz formula is that given, so if I fix Wi or if I just fix Wi, there's a maximal possible genus. The way to see this is that if you consider in this cartoon picture, not just taking the preimage of a generic point, but you take a preimage of one of these critical points, then at the critical point, you get a bunch of sheets which say intersect each other. But since you're counting with multiplicity, that counts as, say, W sheets. So you have Wi sheets here and then some more, potentially, which are disconnected. And so n has to be greater than or equal to Wi for each I. But we know how to express n in terms of the Wi, and you can take this inequality and rearrange it. And you find that the genus is less than or equal to some j not equal to I, Wj over 2 minus Wi over 2 plus 1 minus n over 2, where n is the number of critical points. So this tells you that for any given configurations of W of these critical points, then there's a maximum genus that's allowed as a covering map. And in particular, if you consider, so going back to the string theory picture, so we have these correlation functions. So they look something like this. These correlation functions have a maximal genus. Which means for each given amplitude you want to calculate, so an amplitude in string theory is going to be a sum over your genera, some G string to the Euler characteristic, or maybe minus the Euler characteristic, I always forget, times these correlation functions, that this sum has to truncate. So in particular, every single correlation function, or every amplitude that you would want to compute on the world sheet, has some maximum power in perturbation theory that you could expand to. And this is seen very simply just from the Riemann-Hurwitz formula. So as soon as you can prove that correlation functions on the world sheet only exist whenever the world sheet admits the structure of a covering space, then you can show that the amplitudes truncate in perturbation theory. Now, the next and last thing I want to mention, which is also on the problem sheet, is exactly how these things localize. So if we fix xi and wi,
Bob, can I ask a question?
Absolutely.
On the previous point, so then we also have to have the same effect from the CFT side, that the 1 over n expansion truncates.
Yes.
And so this is well understood from this perturbation theory with twisted sector operators.
Yeah. So this is essentially just the fact that when you're computing correlation functions in the dual CFT, so you have some correlation function, that this is a sum over covering maps. And
it's the same, of course, it's maps.
Yeah. And there's some n dependence, and then some conformal factors coming from the covering map. And so just from that perspective alone, the fact that you have a maximum genus for the covering map tells you that this series truncates in the 1 over n expansion.
Yes, thanks. Yeah, it's the same argument in both sides. Yeah,
Exactly. Yeah. That's one very nice thing about this particular incarnation of AdS CFT is that arguments on one side are almost always the exact same argument on the other side. Once you've understood this, this correspondence in terms of covering maps. So now say I fix xi and wi, so the ingredients that you put in if you want to calculate a correlation function in the symmetric orbifold, you can ask when does gamma exist? And the answer is very simple. So each point in the sphere has n pre-images. So in particular, if we take this point to be infinity, then that tells you that gamma has exactly n points, which are mapped to infinity. So gamma has n poles. And if we take the, let's say we take the simplest scenario where gamma maps from the sphere to the sphere. So we're taking genus 0. Then that means that gamma can be written as a ratio of polynomials, say q over p. And if you assume that gamma is finite at infinity, so that none of those poles are at infinity, this essentially means that both of these have order n. And so you essentially have 2n plus 1. You have 2n plus 1, let's call them unknowns, in your construction of the covering map, corresponding to the zeros here, the poles here, and the overall normalization out front. But then you have constraints, which is that gamma has to have the appropriate local behavior. And the problem on the problem sheet, so the problem sheet is basically to show that the number of constraints minus the number of unknowns is n minus 3. So if you wanted to construct a covering map for, say, 4 points, you have an over-constrained system that you would need to solve. And so for that to have a solution, you need to fine-tune n minus 3 parameters. And these parameters are exactly the moduli on, say, the n-punctured sphere. And one can go through the same argument. So at genus greater than 0, you can do the same thing and show that the constraints minus the unknowns is n plus 3g minus 3. And this is the dimension of the moduli space of a genus G surface with n punctures. And so the fact that you need to fine-tune the number of parameters, which is equal to the number of moduli, tells you that, at least on a naive level, that these objects should localize to points on the moduli space, to some discrete points. And that's essentially everything I had to say about covering maps, so I will open the floor to discussion about anything at this point.
Thank you. Thank you very much for this nice explanation.
Yes, Dimitri.
Yes, I would like to maybe understand a little bit better what's the consequence of this word identity that was derived during the lecture by Matthias. And so in particular, it showed that in certain cases when this covering map does not exist, this is a certain constraint on the correlation functions.
Yes.
what is really the consequences and conclusion in this case?
Yes, so the basic idea of this ward identity analysis is that you introduce, let's say, functions, I'm going to call them omega plus and minus, which are basically correlators with, say, W fields inserted and the vertex operators. So these W fields, basically you can renormalize them. So where does W have a zero? It has zeros when Z is equal to U alpha, because the OPE of U alpha with Xi is linear. And so you can get rid of these zeros by just dividing out by appropriate terms. And then it has poles where Xi is equal to, or where Z goes to Zi. And so you can also factor these out. And the poles have order W plus 1 over 2. And then now you have some functions which have no poles. And basically, if you treat these as polynomials, they have order n. So if you look at the behavior near infinity, they go like Z to the n near infinity. So they're basically polynomials in Z. And these obey constraints. So as Matthias was saying, which direction does this go in? I think it's this one. If you take this combination, so you combine the Xi minus and Xi plus with an appropriate factor Xi, and you take the OPE of the ith vertex operator, this is regular. And these are exactly the same constraints. If you now think about this in terms of not the Xi's and Xi plus, but instead of these P plus or minus now satisfy these constraints. This should be Wi minus 1 over 2. And if you look to the definition of the covering map as, say, a ratio of polynomials of order n, so say instead of writing it as P over Q, write it as, say, minus P minus over P plus, this condition becomes exactly this condition. And so from this sense, you can argue that P plus and P minus satisfy the exact same algebraic conditions as the numerator and denominator of the covering map. And so in that way, if a covering map doesn't exist, then there is no non-trivial solution to these equations.
I think the conclusion was that I think P plus in this case has to be trivially 0.
Yes. So if no covering map exists, then P plus has to be trivially 0 in order for this to be satisfied. And the consequence of that is that the correlation functions without any Xi insertions have to be 0. So if P plus of Z identically 0, this implies that correlators. So just the correlators without the Xi plus, Xi minus insertions, those also have to vanish identically.
So is this something you can prove, or?
Yes. Yes, so this comes from the fact that if you take the OPE of Xi plus with, say, and maybe now I need to write in M1 and M2 labels. So if you take the OPE here, this is going to look like, well, it's got a large pole. Maybe I shouldn't use Z for both. Maybe I'll use Y. So this has a large pole of order W plus 1 over 2. And then this shifts the value of M2 up by 1. So this is basically the statement that psi plus 0 acting on M1, M2 is equal to M1, M2 plus 1/2. Sort of the definition of the zero mode on these states. And then plus things that are regular. So if you try to expand P plus around the point, say, Zi, then you would end up with a correlation function. So P plus Z, it's going to look like Z minus Zi. So now we're taking the OPE near the ith vertex operator, Wi plus 1 over 2, and then a correlation function with, say, VWI, M1I, M2I plus 1/2, and then the rest. Wherever they are. And I'm omitting the W fields. So now if P is identically 0, then its higher order pole also has to be 0. And so you can argue that this correlation function has to be 0. But this is just the old correlation function, the only difference being that this quantum number has been shifted up by 1/2.
Okay, thanks.
Yeah. Yes, Lucas.
Yeah, it's about what you wrote in the beginning, the constraint minus the number of. So
yes.
Yeah, so this seems a lot like index theorem. Is related to index theorem of some differential or not? Some holomorphic differential might be associated to the constraints and the unknowns and the numbers. It's like BC growth system.
I don't know if this is related to an index theorem, but this is essentially the Riemann-Roch theorem. So this can be argued from Riemann-Roch. So you have some dimension. So you might ask, what's the dimension of such maps, or of the space of such maps? And the dimension you find is negative, and it's negative n minus 3. So that's the virtual dimension that you would calculate using Riemann-Roch. And in order to actually pick out a solution from that, then you have to fine-tune n minus 3 moduli. But if it's related to some index theorem, I don't know. I mean, maybe in the way that Riemann-Roch is related to an index theorem, potentially.
Okay, thank you.
Of course.
Okay, Bob, I have another question. So if you want to compute, so the boundary CFT, of course, the simplest thing is to put it on the sphere, but there's no reason why you cannot also consider the boundary CFT on a higher genus.
Yes.
So how does that change the story? I don't know if you already thought about it.
So this is something that's been worked out by Lorentz, actually. So basically, you can consider spacetimes, so where you don't have ADS3, but maybe you have thermal ADS3, whose boundary is a torus. Or you can have other topological constructions which are locally ADS3, but globally have some non-trivial topology, and their boundary is going to be some higher genus Riemann surface. And in that case, you do end up localizing to situations where you go from a surface of one genus to a surface of another, where then this is the world sheet. And this is the boundary. So this was worked out by Lawrence Eberhardt. And I think it's this year. So this paper came out in maybe January or February.
I see, but the story of still writing everything in terms of covering maps goes through. It's just
yes.
More complex covering maps.
Yeah, and the story of writing everything in terms of free fields also works out in roughly the same way. Except now, instead of having free fields which generate global AdS3, you have free fields which generate some coset of AdS3. And that adds some complications to the world sheet theory, but
yeah, it's too hot here, so I have the window open. Sorry for that.
Yeah, I should do the same thing.
So last chance to ask questions to Bob. Any more questions? Everybody is working hard on the exercises.
Yeah, I can tell. I can tell.
Well, anyway, maybe it's actually good to have a little break if there is really no more questions.
Yeah.
We can take a 5-minute break. So let's also thank Bob for this excellent lecture compliment.
Thank you.
And of course, you can continue the discussion on Slack. So once you actually do the exercises, if you have questions, you can post your questions. And well, here there is no official break, but maybe we can have a technical break, 4 minutes, and then we start at 5 with the discussion of Anna.